In this video, we're going to finish the Using Statistical Models worksheet on the KutaSoftware website under the Infinite Algebra 1 section, picking up on the last page, finishing numbers 3 and 4. Now, what we're doing on this worksheet is we're looking at different models or different data sets and then answering the questions associated with each. So in number 3, we have the time for the fastest runner for their age in the Marine Corps Marathon, and it's given for several ages below. Now this can be modeled by the equation y equals 0.111x squared minus 8.1x plus 299, where x represents the age and y represents the time in minutes. So number A says, using this model, what would be the time for the fastest 41-year-old? Round our answer to the nearest hundredth. So remember, age is represented by our x values. So we're going to use this quadratic equation, which best fits that model, plug in x and solve for y, because we're solving for that fastest time. So y equals 0.111 x squared, where x is 41, so 41 squared, minus 8.1 times 41 plus 299. So typing that into our calculator, 0.111 times 41 squared equals 186.591. So from that, we're going to subtract 8.1 times 41, which is 332.1, and then finally we're going to add 299. So 186.591 minus 332.1 plus 299 equals 153.491, which rounds to 0.49. And this is the time in minutes, so we cannot forget our label. 153.49 minutes is our solution. So that's the fastest time for a 41-year-old. So looking at our model, if we were to graph 153.49 at 41, you can see that it falls on that quadratic function. Now let's look at B. B says that according to the model, what would be the fastest time for an 83-year-old? So now we're going to plug 83 in for x. So y equals 0.111 times 83 squared minus 8.1 times 83 plus 299. So typing all that into our calculator, 0.111 times 83 squared minus 8.1 times 83 plus 299 will get 391.379, which rounds to the nearest hundredth to 391.38, and that's in minutes. So the fastest 83-year-old, their time would be 391.38 minutes. And then finally, the last question associated with this data is C, and it says what age or ages correspond to a time of 171 minutes. We're to round our answer to the nearest tenth. So now, as opposed to plugging in x values, we're going to plug in 171 for y and solve for x. So we'll have 171 equal to 0.111 times x squared minus 8.1x plus 299. Now in order to solve for this, I'm going to set it up so that we have a quadratic equal to 0 so that I can use the quadratic formula. So I'll subtract 171 from both sides in order to accomplish this. So I'll get that 0 is equal to 0.111 x squared minus 8.1x plus 299 minus 171 will be 128. So plus 128. So from this, you can see that I have an A value of 0.111, I have a B value of negative 8.1, and a C value of 128. So let's plug those into our quadratic formula. We'll have the opposite of B, which is 8.1 plus or minus the square root of B squared which is 8.1 squared, minus 4 times A, which is 0.111, times C, which is 128, all over 2 times A, which will be 0.222. So I'll have 8.1 plus or minus 8.1 squared is 65.61, and when I subtract 4 times 0.111 times 128, I'll get a positive 8.778. So we're going to be taking the square root of 8.778, which, taking the square root, will give me approximately 2.963. So 8.1 plus or minus 2.963 all over 0.222. So we'll get two separate answers. If we take 8.1 and add 2.963, then divide it by 0.222, we will get 49.83, which we will be rounding to the nearest tenth. So that's going to be 49.8. So 49.8 years. And then if we take 8.1 and subtract 2.963 and then divide by 0.222, we'll get 23.13, which rounds to 23.1. So for C, we get two different ages that have a time of 171. That's 49.8 years and 23.1 years. So if we look back up at our table, for a time of 171, which is directly above a time of 170, you can see that our points do indeed fall around 23.1 and 49.8. Now, continuing on to number 4, our problem says that economists have found that the amount of corruption in a country is correlated to the productivity of that country. So productivity is measured by gross domestic product, otherwise known as the GDP, and that's per capita. Corruption is measured on a scale from 0 to 100, with 0 being highly corrupt and 100 being the least corrupt. So our data can be modeled by a linear equation. Y equals 525x minus 9,640, where x is that corruption score and y is the gross domestic product per capita. So part A says, according to the model, what would the GDP per capita of a country with a corruption score of 38 be? Now remember, corruption score was represented by our x values, and GDP is represented by y values. So we're going to plug in an x value of 38 and solve for y. So using our line of best fit, we have y equal to 525 times x, which we're plugging in a value of 38 for x, and then we'll subtract 9,640. So 525 times 38 equals 19,950, and from that, we're taking away 9,640. And that will give us an answer of 10,310, and our gross domestic product is in dollars. So our label is $10,310. That is our solution for part A. Part B, it says, using this model, a country with a corruption score of 75 would have what GDP per capita? So again, we're plugging in our x value of 75 and solving for our GDP, y. So y will equal 525 times, as opposed to 38, this time we're going to be using 75. And then we're going to subtract 9,640. So 525 times 75 equals 39,375. And when we subtract 9,640 from that, we will get $29,735 for our GDP. And note that in part B, our GDP was greater than part A because remember the correlation. The economists found that the amount of corruption is correlated to the productivity. So the more corrupt a country is, the closer to 0, the less productive that country is. The less corrupt, which is closer to 100, the more productive that country is. So that's why a corruption score of closer to 0 gives a lesser GDP, whereas a corruption score of closer to 100 gives a higher GDP. Now C says that a GDP per capita of $17,000 corresponds to what corruption score according to the model? So now we're given our Y value, so we need to solve for our corruption score X. So if we're given a Y value of 17,000, we'll take 17,000, plug that in for Y in our line of best fit, and that's going to be equal to 525 times X, which is what we're solving for, minus 9,640. So we'll add 9,640 to both sides in order to get the term with X all by itself. 17,000 plus 9,640 equals 26,640, and that's going to be equal to 525 times X. So dividing by 525 will help us isolate that X and give us our corruption score. So dividing 26,640 by 525, we will get 50.74 equal to X. However, we're rounding to the nearest whole number, and 50.74 will round up to 51. So our corruption score for a GDP per capita of $17,000 is 51. And with that, we wrap up the Using Statistical Models worksheet. Like always, leave a comment below if you have any questions or want to leave me a note. And don't forget to like this video and subscribe to my channel. All likes and subscriptions are greatly appreciated, and just let me know that you're finding these videos useful. So don't forget to like, subscribe, and share before moving on to another video.